and sports analytics in R. Today we're going to be building the player load function. Player load is a metric that is returned in arbitrary units. It is oftentimes returned with catapult data and has gained recent popularity in the literature where individuals or researchers try to assess player load and quantify match demands for players in rugby and soccer typically. So what we're going to be doing is building this function here. The instantaneous player load formula is at the top. This is taken straight from the Catapult website. And what the value is, or how it's calculated rather, is by taking the acceleration in all three axes, X, Y, and Z, at the current time point, minus the one that just happened before it, and taking that squared value, the summation of the squared values, and square rooting it. So basically what they're doing is taking the time point right now less the time point earlier, that entire vector in all three planes, and taking the square root of that, which is equivalent to the Pythagorean theorem where ax squared plus bx, a squared plus b squared equals c squared. It's along the same lines as that. And then what we're going to be doing is building the accumulated player load formula, which is the summation of all of those. In this photo, you don't see it, but on their website, it does state to correct it for the sampling rate, which is typically, in their case, 100 hertz. So what we would do is take this value and divide it by 100. So here we'll start. This is going to be pretty simple. I think it's about 20 or 30 lines of code total, plus some empty lines for clarity. So what we're going to be doing is let's build 10 seconds of playtime here. So we're going to be creating our data set, unlike the metabolic power function that we were using actual data. And that's because this data it is formulated off of actual soccer data that I have, but unfortunately that data is proprietary. So what we're going to do is just model our data that we're creating off of actual data. So let's set our seed, and what that does is ensures that the random numbers that are generated on my end are going to be the exact same numbers that are generated on your end. So we'll build our data set. We'll call it IMU data. And this is going to have 4 variables: game duration, or game time. And that's going to be 1 to 1000, which is at 100 hertz, just 10 seconds of game time. Our acceleration in the x-axis, which will be 1000 values with a mean value of 0 and a standard deviation of 1.25. Our y-axis is very similar, our norm, which is random values with a normal distribution, 1000 values, 0 mean, and 1.1 as a standard deviation. And in our z-axis, sorry about that, there we go, our norm, 1000, 0, and 0.8. So if we want to check this out here, head, which will return the top 6 rows of our values, are here. We do see that there are a few negative values, but these are going to be returned as positive once the values are squared and then square rooted. So for curiosity's sake, let's look at a histogram, which is going to be the distribution of our values. So we'll do just of AX here. And there we have it. And this is pretty similar to the values returned in the actual soccer data that I have. So let's start working on our player load function. We're going to call it just player load right here. And we're going to need to build our function with acceleration in AX, AY, and AZ. If you have, just for, if you have the R version 4.1.0 or above, you could also write your function as, and this is just new notation, player load, and then you have a backslash, and then AX, AY, AZ, and then you would open up your curly brackets. But that's just for curiosity's sake, or just so you can learn how to write things a little bit faster, because it's a little bit more shorthand. So we're going to be building some vectors, and what that's going to do is allow us to easily calculate the difference in X, Y, and Z metrics at the current time point and the one before. So difference of difference of AX, we have our difference AY. So what this diff function is doing is going to take the value minus the value before it. So that's exactly what we need within our player load function. So, and we're going to do that in all three axes. So diff AZ. And we want player load, which is going to equal, so you can either use an arrow or an equal sign, it doesn't matter, the square root of, and then here we have difference of X, or AX rather, squared, plus the difference of AY squared, plus the difference of AZ squared. And then because we're at 100 hertz, we divide it by 100. And then the value we want returned is player load. And then we hit enter. Oh, and we have to close that bracket first. And then we hit enter. So then we have in our environment, player load and IMU data right here. So we're going to want to add this onto our current IMU data set. What we will do is build a new data set, so that way we don't overwrite our current data. But first we're going to just create a vector of these three values, so that way we can just add on the vector itself rather than have to build this whole new data set and rewrite all of this with comma and then stuff over here. So let's just remove that. So we're going to call it game load just for clarity's sake, that we don't call it player load and then overwrite our function. So game load is going to be player load, and then we have here IMU data, and then we're going to choose the column that fits our AX, AY, and AZ arguments. So IMU data and then AY, and these $signs are simply just telling R to select or choose this column within this data set, and we'll hit enter here. So what we now want to do is try to add the two together, right? So IMU data, and we'll call it updated, and we're going to cbind, which is bind columns together. So the columns on the left that we're going to use are IMU data and our game load. And this will return an error. And that's because we have 999 values in our game load value, vector rather. And that's because that first value is not there. So essentially we only start from time point 2. So what we're going to have to do is add on a 0 right at the beginning. So game load will overwrite that by adding a 0 to our current game load. And then if we see right here, now we have 1,000 observations right there. So now we can add that together. And we see right here, game data updated is 1,000 observations of 5 variables because we've now added on this game load variable as well. So if we want to look at that, we can do head game load. Oops. Sorry, IMU updated rather. Data updated. And then we have our game load. What you could have also done was something like this, IMU underscore data updated, and then game load, and then just added on our game load, and that would result in the same thing. So I'm just going to comment that out just to make sure that we don't have redundancies or get mixed up. Finally, what we're going to do is we want that cumulative player load value. So we're going to explicitly state, I want to make a new variable called game load accumulated or cumulative, and we're going to use the cumulative summation function, which, like we used in the metabolic power function that we built, it adds up all the values from a certain time point and before it. So if we have values 1 to 10, we have 0, and then 1 plus 0, 2 plus 1 plus 0, and so on. So we have, and then we're going to say, okay, take the cumulative summation of our current game load. And then if we wanted to take a quick look at that, IMU updated, and now we have this here. So this is exactly what it is saying. So 0.0072, and then add that to 0.025, and we get 0.033. So we do get this cumulative summation, and let's finally take a look at this. So we're going to plot, and then what we want is our player load, or game load rather. So that's our Y variable. Our X variable is going to be game duration. Let's just make sure that I'm calling that correctly. Yep. And then our data is going to be IMU, and then hit that. And there we go. So this is 1,000 values of our game load over, and what this is actually 10 seconds of playtime. And then finally, if we want to look at the cumulative player load, so we have game load accumulated over time with data equaling IMU data updated. And there we have it. And that's exactly what you'll see in the literature, is basically just a straight line over time. And then if there's a halftime or some dead time, this will kind of plateau before increasing again. And there you go. That's player load. If you don't have player load in all 3 axes, and you only have it in the horizontal axis, I would assume, because it's returned in arbitrary units, that you can use this the exact same way as long as it remains consistent across all of your data sets per player. So that way you can create these models based on your player load consistently without returning errors or returning values that are inflated because of one axis versus all 3 axes. If you have any questions or comments, let me know. You can reach me at aaron@midsprint.io right here. On most social media platforms, Twitter especially, at Aaron Z. Pearson. And then finally, I have all of my screencasts at twitch.tv/Aaron Z. Pearson. For an archive, go through the highlights. I've highlighted all of I've maintained an archive of all the previous screencasts. Right now, there's only one, which is our metabolic power function. Thanks.